Good morning. Today we're going to be solving some more problems on the displacement method, application of the displace method, and I'm going to take up a specific problem. Okay. Now, if you look at this particular problem, this is the problem, and the various questions are that one, find this displacement, and second, find this rotation, and third, bending moment. So in other words, I'll call this as R1, R2. So the question is 1, find R1 and R2, and 2, draw bending moment diagram. Okay, so this is the problem statement. Now let's see how we can go about solving this problem. So first and foremost, actually let's find out, let me go back to that problem itself. The first thing is to find out the degrees of freedom. So A, B, C. So what we have is unconstrained degrees of freedom are equal to 3 into 3, 9. Restraints, 3 here and 2 there, minus 5. Constraints, 2 members, 1 into 2, axial rigidity, minus 2, so this is equal to 2 degrees of freedom, and the 2 degrees of freedom are R1 and R2. These are the displacements corresponding to degrees of freedom. Okay? So what's the next step? Step 2. For AB, what is the equation? Member force deformation, M. So I'm going to write it down for AB. MAB is equal to 4EI by L theta AB plus 2EI by L. So we are doing the member deformation relationships, and for AB, MAB is equal to 4EI upon L theta AB plus 2EI upon L theta BA plus fixed end moment AB. Then MBA is equal to 2EI upon L theta AB plus 4EI upon L theta BA plus fixed end moment BA. Now here, what are the fixed end moments? Fixed end moment of AB is equal to 0, and which is equal to fixed end moment of BA. Why is that? That's because there is no member load on AB. And since there is no member load on AB, fixed end moments are automatically equal to 0. Now we look at BC. MBC is equal to 4EI by L theta BC plus 2EI by L theta CB plus fixed end moment BC, and MCB is equal to 2BI L theta BC plus 4EI upon L theta CB plus fixed end moment at CB. Now note here that if you look at the end, this is fixed, so therefore AB is normal, and in BC, C is a fixed roller. So when it's fixed, there is a moment. Since there's a moment, we have to use the original. If this had been a hinge, then of course we would have used the modified, but in this particular case it is not, and therefore we're going to have it continued this way. Okay, what about fixed end moment at BC? Now that we have to find out. Okay, and let us find that out. So next step is a fixed end moment at BC and CB is going to be there because in member BC there is a load in the member. So we have to find out what that is. And how do we find that out? Well, note that there is a slight difference here. The member is inclined, the loading is this way. So I can actually write this load of 100. See, this is 3, 4, 5 triangle, and therefore if I write down the vertical component and the horizontal component, the vertical component of this is going to be 80 and the horizontal component is going to be 60. Now the horizontal component, since the member is actually rigid, does absolutely nothing, and therefore if you look at it, this problem essentially becomes one where you have a 10 meter with 80 kilonewton, and we have to find out for B and C what the fixed end moments are, and that we know is equal to PL by 8. So if you look at that, that becomes 100 kilonewton meter, 100 kilonewton meter. This implies that fixed end moment BC is equal to 100 kilonewton per meter, and fixed end moment at CB is equal to minus 100 kilonewton meter. Okay? So this is something that we know as of now. Okay? So now what's the next step? We've written the member end deformations, we've found out the fixed end moments. The next step is to find out for each degree of freedom, you have to find out the kinematic relationship, the relationship between the member end deformations and the structural degrees of freedom. And for that, how do we do it? Well, kinematics. So therefore, the first step is this. Right? And give R1 equal to 1 and R2 equal to 0. So if we give that, what happens? So this point is to move up by 1. Now this point can only move up because that's the only direction that it can go in. So this goes up. Now how do I find out where this point goes? See, this is the important, this is what I said by kinematics. So therefore, what we do is, we let that go up by 1. That's the only way it can go. So this point we know. We know where this point is. Where is this point? This is fixed, and therefore it's not going to go anywhere. Okay. How can this point go? This point can actually go on this. Okay. So now let us look at this carefully. What we have to do is, now if since I have taken this up by 1, okay, actually if you look at it, the components of this 1, okay, this is vertical, along the member and perpendicular to the member. These are the two things that we have to find out. And if you find that out with the 3, 4, 5 triangle, please do the equal triangles. You'll see that this is 3 by 5 and this is 4 by 5. In other words, what has actually happened is, suppose this point were not fixed, this could have gone up also with it by the same amount. Okay, so now here the point to be noted is that in actual fact what has happened is that it has gone along this way and this way. Okay, now but this, this point cannot go there, right? If you look at this, that means this member has become something like this, if we displace it. But this cannot go there because this point can only move along this line. Okay, so what has to happen? Since this member is this way, the only way this member can move is along this. And when we take it along this is the point at which it is going to get the cut. And that is the point where this member is going to be. Now what is that point going to be? Let us look at that. Okay, if we look at this, you have to understand that this is 1. Okay, now this, if you look at this is a 3, 4, 5 triangle. So if 4 is 1, that means this is going to be equal to 3 by 4, and this total distance is going to be 5 by 4. Okay, so once I know this point, I can draw now my displaced shape. My displaced shape, note that this cannot rotate. So this remains straight, and this also has to remain parallel to the line. So the thing will go in. And here also it cannot rotate. So this is our rotation. Now, if we look at this from the chord, okay, so if we look at this angle gives theta AB. And what is that angle equal to? You will see that theta AB from the chord to the tangent anti-clockwise. So it's going to be plus 3 by 4 is the displacement and 10. So theta B is going to be 3 by 40. What about theta BA? Same thing, 3 by 40. And positive from the chord to the tangent plus 3 by 40. What about this one? If you look at this, the total displacement of this is 5 by 4. Okay, this has moved by 5 by 4. And what is the length? 10. So therefore, theta BC is going to be equal to, now look, from the chord to the tangent, what is it? Minus. So we're going to have, because it's clockwise, from the chord to from the chord clockwise. So this is going to be minus 5 by 4 divided by 10. This is going to be minus 5 by 40, and theta CB is the same. Okay? So we have found out theta AB, BA, BC and CB in terms of R1. Okay, when R1 is equal to 1, these are the values. Okay, similarly now R2 is much easier. So this is my R1 equal to 1. So I'm going to just put it around it. All these computations are for R1, and for R2 equal to 1 and R1 equal to 0, the displacement pattern is going to be very, very simple. It's going to be this, and if you put this, then what do we get as theta AB? Theta AB is equal to 0. Theta BA is equal to plus 1 from the chord to the tangent, that's anticlockwise. Theta BC similarly from the chord to the tangent 1. Theta CB is equal to 0. Okay, so we've done the kinematics, and this kinematics is going to be important even when we do virtual displacement. So remember this kinematics. Okay, so if we look at it, then by substituting the kinematics into the equations, what do we get? For AB, we get MAB is equal to, now 4EIL, now theta AB, now let's put it down, 4EI. What is L? 10. Theta AB, what is theta AB? Theta AB is equal to 3 by 40 R1 plus 0 R2 plus 2EI upon 10. Then we have 3 by 40 R1 plus 1 R2. FEM is 0. MBA is equal to 2EI upon 10, 3 by 40 R1 plus 0 R2 plus 4EI upon 10, 3 by 40 R1 plus 1 R2. So this implies that MAB is equal to 3EI by 100 R1 plus 3EI by 200 R1 plus 2EI by 10 R2, which basically means is equal to 9EI upon 200 R1 plus 2EI upon 10 R2. That's MAB, and similarly MBA is equal to 3 by 200 R1 plus 3 by 100, so we get exactly the same thing. So we get 9 EI by 200 R1 plus 4 EI by 10 R2. These are MAB and MBA in terms of R1, R2. Similarly, we can write down for BC. So let us write down for BC. We get MB BC is equal to 4 EI by L. Theta BC is equal to minus 5 by 40 R1 plus 1 into R2 plus 2 EI, here L is also 10, 2 EI upon 10, theta CB is just minus 5 by 40 R1 plus fixed end moment at BC, and the fixed end moment at BC is plus 100, so it's plus 100. Similarly, MCB is equal to 2 EI upon 10 minus 5 by 40 R1 plus 1 R2 plus 4 EI by 10 minus 5 by 40 R1 and then minus 100. So this then implies that MBC is equal to, it's going to be minus 5 by 100 and then minus 5 by 200. So this is going to become 5 by 100 is 1 upon 20, 1 upon 20, and this is 1 upon 40. So 1 upon 40 is going to be equal to minus 3 upon 40, 3 EI upon 40 R1 plus 4 EI upon 10 R2 plus 100, and MCB is equal to similarly minus 3 EI by 40 R1 plus 2 EI upon 10 R2 minus 100. So this is MCB. So now I've got my MAB, MBA, MBC and MCB. Okay, so now next what I have to do is I have to find out the work done by the loads. So I'm going to write down the virtual work equation. The first virtual work equation is going to be written down for this as virtual displacement. So if I put this as my virtual displacement, then what do I get? I'll get, so first virtual work equation, I'm going to put R1 equal to 1. This is an arbitrary, since it's an arbitrary displacement pattern, I'm going to give the first displacement pattern is going to be this pattern. Okay, so my external work will be whatever the load, okay, into 1. Okay, so what is the external load? If you look at the external load, there is only one external load, which is 50 tons, because that's applied at the joint. So how much displacement does that undergo? If we look at it, if I give this virtual, since the load is applied here and it's undergoing 3/4 in the same direction, the external work done is 50 into 3 by 4. Okay, if you look at everything else, it's going to be what? Think about it. There is no other external load which does work. Okay, so this is the only one that does work, and so this is going to be equal to 75 by 2. This is the external work, kilonewton, and whatever, we can put it as whatever. Okay, now internal virtual work. The internal virtual work is done by all the moments undergoing the rotations. So what is the moment? One moment is MAB. What is the rotation that it undergoes? It's going to be theta AB plus MBA multiplied by theta BA plus MBC multiplied by theta bar BC plus MCB undergoing theta CB. So these are all the moments, and they also take care of the work done by the shears. The only thing left behind is the load 100, which gives rise to reactions at the supports. So what kind of reactions do I get? If you look at it, the reaction that I get is actually equal to 50 and 50 vertical in both the direction. Okay, so I just have to find out what is the work done by each one, each vertical reaction. So if you look at each vertical reaction, okay, the vertical, is this point moving vertically? If you look at it, it is not, it is only moving horizontally. So this one does not do any work. Okay, however this one, this vertical reaction does work. How much work does it do? It does into 1. Okay, so this is going to be equal to plus 50 into 1. Okay, so having written that, this is my internal virtual work. So I can put internal virtual work equal to external virtual work, and if I substitute all the terms that I have, you will see that this essentially becomes the following. Nine EI upon 200 R1 plus 2 EI upon 10 R2 multiplied by, what is theta AB, theta bar AB in terms of R1? It is equal to 3 by 40. Okay, then plus, what is MBA? MBA is equal to 9 EI upon 200. Okay, R1 plus 4 EI upon 10 into 3 by 40. Okay, plus MBC is equal to minus 3 EI upon 40 R1 plus 4 EI by 10 R2 plus 100 multiplied by minus 5 by 40. Note that this work done is multiplied by the rotation being clockwise, it is negative work, plus MCB. MCB is equal to minus 3 EI upon 40 R1 plus 2 EI by 10 R2 minus 100, okay, multiplied by minus 5 by 40. That is all the moments, plus 50 by 1 is equal to 75 by 2. Okay? So that is my first equation. Fairly complex, but I can always simplify it and write it in terms of R1 and R2 and a number. Okay? What about the second one? Second virtual work equation is R1 equal to 0 and R2 equal to 1. This will give me independent. What is external virtual work done? You will see that since that point does not displace, it's going to be equal to 50 into 0, which is 0. Internal virtual work is going to be, again, MAB into theta B, blah, blah, blah. and MAB into theta B is what? 0 plus MBA into theta BA, which is 1, plus MBC into theta CB, which is 1, and plus MCB into theta CB, which is 0, plus the work done by the reactions, which is 0, and therefore what we have, the second equation becomes our most common MBA plus MBC is equal to 0, which we know already. Okay, this is again we got it from virtual work. So therefore, if you notice that the virtual work, when you give a rotation, essentially boils down to the fact of it being the equation of joint B. Okay, and that is what we are interested in. Okay, so now we've written the two equations, and essentially if you note that once I substitute for MBA and MBC, I'll just put them down, you will get that 9 EI by 200 R1 plus 4 EI by 10 R2 minus 3 EI by 40 R1 plus 4 EI by 10 R2 plus 100 is equal to 0. This implies, this is easy to do. So what you get is 515 minus 6 by 200 minus 6 by 200 becomes minus 3 by 100 EI into R1 plus 8 EI by 10 R2 is equal to minus 100. That becomes my second equation. My first equation, if I go through it, let us go through the steps of the first equation. Okay, I'm going to actually now go through this, and what you'll get is, let me put down all the things that we're going to get. So this equation is simple, and the first equation, if I expand this, is going to be equal to 27 by 8000 R1, of course EI, plus 6 EI upon 400 R2 plus 27 EI upon 8000 R1 plus 12 EI upon 400 R2. Then you have minus minus, so it is plus 15 upon 15 EI upon 1600 R1 plus, sorry, minus, because plus into minus is minus, so it's minus 20 upon 400 EI into R2. Then I have minus 500 upon 40. Then I have plus 15 EI upon 1600 R1. Okay, minus 10 upon 400, 10 EI upon 400 R2 plus 500 by 40 plus 50 is equal to 75 by 2. So if I put in all the R1s together, this will give you you will see that if I put 8,000, 8,000, this will become 75, 75, 150, 150 plus 54, so that's 2004, 204 upon 8,000 EI R1, and then all of them are 400, so it's 6 plus 12 is 18, 18 minus 20 is minus 2, minus 12 upon 400, so minus 12 upon 400 is minus 3 upon 100 EI R2 is equal to, this cancels this plus minus and this goes on the other side, so this becomes 100, so this becomes minus 25 by 2. Okay, so we can simplify this, we can divide by 4, so we get 51 upon 2000 EI R1 minus 3 EI by 100 R2 is equal to minus 25. That is one equation. The other equation, so let me write down those two equations, and you will see that those two equations will end up being this way. If I take out the EI, I'll take out EI and I'll write it in matrix form. This will become 51 upon 2000. This is going to be minus 3 upon 100. Here I'm going to have minus 3 upon 100 plus 8 upon 10 multiplied by R1, R2 is equal to minus 25 by 2 minus 100. Note something interesting. You will see that this is equal to this. In fact, that is also always true. That if you write it down properly, this and these are equal to each other and it's symmetric. Okay? And this one, if you look at it, essentially turns out that we can solve for R1 and R2 by taking the inverse of this. So the inverse of this is going to be equal to, if you look at this, this is going to be 20,000, this is going to be 100,000, so this is going to be minus 18 upon 20,000 minus 18, and this is going to be 408. 408. So 408 minus 18 is going to be 390. So this is going to be equal to 20,000 upon 390 EI multiplied by the inverse is 100. Okay, so I can find out R1 and R2. So once I know R1 and R2, okay, then I substitute these back into the original equations. The original equations being MAB is equal to this into R1, MBA is equal to this into R1 and R2, and let me see where my BC is. For BC, MBC is given in R1, R2, MCB is given in R1, R2. So you can find out MBC and MCB. Okay? So now the point comes around that I found out R1 and R2. There are several interesting points to note over here. One, that this can be written in terms of stiffness matrix into R is equal to some force. We will see later when we use them. I'm not, right now, this is not matrix method. I am just writing down two equations which I'm solving using matrix algebra. So this is, I'm just solving two simultaneous equations using matrix algebra. Right now I have not yet introduced you to the concept of the stiffness method. Okay? So understand that I'm still using the displacement method, accepting that I am slowly beginning to introduce the concept of kr is equal to f. This is k, this term is k, this is the r vector, and this is like the equivalent load vector which represents all the effects of all the loads that come in. Now, the whole point here is, let us just assume that I've been able to find out MAB, MBA and MBC. Okay? Now where do I go from there? Okay, so I have substituted, I have found out MAB, this is known, MBA, this is known, MBC, this is known, MCB, this is known. Okay? Now, the point that I would like to make is that I have not written down R1, R2, MAB, MBA, MBC and MCB, the values, just so that I want you to actually solve this problem yourself. Okay? And when you solve this problem yourself, okay, you are going to get the values. Next lecture, just before I start my next lecture, I'm going to give you these values so that you can check whether you have done the problem correctly. I'm just giving you the steps that you have to go through. I'll give you the solution at the beginning of next time so that you have an opportunity to actually try and solve these problems. Now, once you know these, let me just go back to what I was trying to state. That ultimately, how you get your bending moment diagram is this way. That you know MAB, you know MBA, you know MBC, and you know MCB. Okay? Note that over here, what do you have? You have this load, okay? And over here, what are the things that you have? Note that at this point, I know that there is not going to be any vertical reaction. Why is that? Because it's a roller. So what's the only force that's going to come? This is what I'm trying to say. Be innovative. Incorporate. Don't try to solve problems just by themselves. Okay? Here you know that since this is a roller in this direction, you're not going to have any... okay, let me just put it. This is, since I'm being very, very... What I have over here is MA, VA, HA, and then I have this over here. So here I'm going to have MC, and the reaction is going to be just HC because vertical cannot be there. Since this is going to be this way, you might as well apply this. You might as well apply this. The fact that it's going to be like this. Okay? So, might as well apply that this is going to be HC and it's only going to be vertical. Since this is going to be vertical, I know that over here I'm going to get both a horizontal and vertical. Okay? Now note, these are not the shear and this is not the axial force. I'm just trying to be absolutely, so once I evaluate these, I can actually evaluate all the support reactions. So what is this going to be equal to? If you look at this is going to be equal to 100. So this is going to be 100, then this is going to be 100, this is going to be 100, so this is going to be 100. So over here, this is going to be 100. Okay, now here I have this, so this is going to be here, this is going to be here, so this is going to be this way, this is going to be here, and so here I have 50. So one of the other equations that I get is HA plus 50 is equal to HC. Okay? Now can I find out HA? Sure, I can find out HA. Why? Because if you look at it, HA is equal to, now look at this, if this way, then over here also it's this way. Okay? So HA is going to be equal to MBA plus MAB minus, because if you look at it, both of them give the same. So it's going to be minus upon 10. So that is my HA. Now these two I know, so I can find out HA. Once I know HA, I can find out HC. Okay, so I've got my horizontal. I know this, I know this. I know this, I know this, I found out this. Once I have all of those, I know all of these, I can draw the bending moment diagram. I leave it up to you. I'll draw the bending moment diagram next time. Okay? So now what I want to do is I want to bring to you a concept, and I would like you to solve this problem yourself, and I'll come back next time and solve the problem. What I want to do is, now I've done enough problems in using the displacement method, that I am now going to propose problems and for you to do, and then once you have done the problem, I'm going to go back, look at my next lecture, and you'll get an opportunity to find out how to do the problem correctly. But I recommend that before you look at the next lecture, I would suggest that this you solve completely. I'm going to give you the answers next time. Okay? And I would like you to look at one other problem. Let us look at what the problem I would like you to look at. Looks suspiciously like the problem that we solved today, didn't we? Excepting that I have made a small change. This is A, this is B, this is C. What I have done is I have made this fixed roller into a hinge roller support. Okay? And I'm still going to say that you have to solve this problem using these and these two displacements as your degrees of freedom. Why? Actually in this particular case you have a third degree of freedom, but remember this is an end hinge, so I can actually treat BC, okay, as a modified member and keep AB as an original member. So BC is a modified member with a fixed at this end and a roller at this end. Okay? So what I would like you to do is, given this problem, 1, find R1 and R2, 2, draw bending moment diagram. Exactly the same problem as I have done. So I am leaving you at the end of this lecture with two things to do. This is the first assignment that I would like you to do in displacement method. Please go ahead and solve the problems. First problem, having done everything, find out R1 and R2 and then draw the bending moment diagram using the procedure that I have outlined. Second, take this problem, solve this problem through, okay, and find out R1 and R2 and draw the bending moment diagram. I am going to give you the answer to this and solve this next time. And another interesting point that I am going to bring out, and this is of course what I tend to do always, and that is not just the ability to solve problems, but you see what I have done over here is I have changed a fixed into a hinge. So I am going to actually look at next time how the effect of changing support conditions what effect does that have on the displacements and the bending moment diagram in the structure at all times. Okay? So therefore, one aspect that I would like you to look at when you're doing this assignment is not just get the numbers, but once you get the numbers, you also try to see what effect, because I've got exactly the same member with exactly the same load, and since I have the same member and the same load, okay, the only difference here is this support condition. So this difference between the two answers is going to give you the effect of changing this fixed to hinge, and that is something that I am going to concentrate on the next time. Thank you very much. Do please solve the problems, and if you want to know how the problems and their answers are, wait for my next lecture. Thank you. Bye.